let's move to the last speaker of this morning, Professor Eenoo. Professor Eenoo is professor at Ghent University, also director of the Belgian IOC accredited antidoping laboratory, which is called DoColab. He's past president of the World Association of Antidoping Scientists and chairman of the Quality Assurance Committee of this association. He's also a member of the Health, Medical and Research Committee of WADA and a member of the Anti-Doping Commission of the Belgian Olympic and Interferon Committee. His lecture is entitled WADA Accredited Laboratory ANNO 2017. Please.
Okay, thank you very much, Chairman. First of all, I would like to thank the Royal Academy for inviting me to speak here today on something for which I am very passionate about, the fight against doping. I am very fortunate, unfortunate some might say, to be the last speaker, but I think it's very fortunate because you've been introduced in an excellent way, so I will be able to skip a few slides or go very fast on a few topics, which leave me some time to become a little bit more technical on some aspects, and I hope you bear with me on those technical aspects. First of all, I would like to give a general introduction on what WADA accredited labs are, because sometimes there's a misconception. First of all, the reason for the existence of WADA. WADA was founded in 1999, as you have heard, and became operational in 2000. And the main reason why WADA was founded is given on this slide, but actually it comes down to harmonization of rules. Prior to WADA, IOC was governing international sports at the Olympic Games, but every international federation had its own rules. Every country had its own anti-doping rules. And there was legal uncertainty for athletes when competing, for example, in Flanders, about the situation of ephedrine if they were cyclists, because the International Cycling Union had a threshold, the Flemish community did not have so. So there were huge differences, and WADA was put in place to harmonize the rules, and one of the other things they needed to do was accredit labs. So they needed to take over the role of the International Olympic Committee and found a set of rules by which labs had to obey by. Now, how they did this was, first of all, they introduced the World Anti-Doping Code, and we have had several versions of this. This is kind of the constitution in anti-doping. It sets the general framework for how other anti-doping rules will get into place. Because the anti-doping code as a constitution is followed up by several international standards. International standards for testing, which will describe how we need to collect samples, international standards on privacy, for example, but most important for us as labs, the international standard for laboratories. Again, it is a general document which will set the general framework for the accreditation and operation of WADA accredited labs. This is then complemented by a huge number of technical documents, model guidelines and rules. And if you bear with me, if you look at the dates, you will see we have quite a dynamic system. Technical documents change quite rapidly, so I do not agree always with the comment, why don't they apply this technique or that technique? We do apply it, and very, very rapidly. Much more rapid than you might have thought earlier during the presentations. These rules change very rapidly, but of course we need to make sure that all of our methods and all of our techniques are validated. Now, the international standard for laboratories and how to become an accredited laboratory, how does it work? Well, first of all, if you want to become a WADA accredited laboratory, you need to have ISO 17025 accreditation. It's an independent type of accreditation in Belgium done by the Ministry of Economic Affairs. BELAC comes around and audits labs, checks that all methods are validated and that you follow very nice international standards regarding quality. On top of that, as I've said, you need to comply with the international standard for laboratories, its technical documents, model rules and guidelines, which are not only technical, as you might expect, but also administrative. For example, we need to spend 7% of our budget at least on research. And this is of course also a financial one. So you have administrative ones, financial ones, and of course most of all, for the analytical chemist, the most important one, the technical aspects. Well, WADA sets the general framework, but anybody can claim that they fulfill the general framework. So what they do on top of that is they have an external quality assessment scheme, which is a proficiency test. They test if laboratories fulfill the criteria by sending test samples. And the system they have in place for this testing is very stringent, and I will go into detail in the next slides. Finally, as part of the ISL, there's an ethical code. So if anybody of you would have a question about a particular case which is still pending, for which no decision has been made, I will need to say that I cannot answer that question. At the same time, it limits the laboratories in what they can do. Just as an example, we cannot do supplement testing anymore because there might be a conflict of interest, so we are very limited in the type of samples we can analyze. Often, we get requests from clinical laboratories to test the sample for the presence of anabolic steroids or stimulants, and of course we need to decline this, because this is not an anti-doping sample, and it might be just a well-known cyclist, soccer player, athlete, trying to check whether or not we can detect a prohibited substance. So we can only accept samples coming from official WADA code compliant organizations. Now, if I was talking about the external quality assessment scheme, the proficiency testing scheme, how does it work? Well, at least 3 times per year we get announced 5 samples from WADA. This might be blank samples, this might be samples to which they have added prohibited substances or post-administration samples. And we need to analyze those samples and report results. We also need to report for every sample the steroid profile, which is a number of endogenous steroids and ratios of these endogenous steroids, the specific gravity and the pH. The latter 2, of course, are the easiest ones. Threshold substances, this means substances which are only prohibited if the concentration exceeds a certain concentration, might be added, and also non-threshold substances. These are substances which are prohibited at any concentration. For each of these classes of substances, WADA has put in place minimum required performance limits, levels we need to be able to detect, and you have just heard that some of these are as low or even lower than a sugar cube in an Olympic swimming pool, and in general they will also add them at this concentration. So they test us at the concentration they ask from us that we are capable of doing it. Now, as anybody among you knows that if you have an examination, you might prepare a little bit better than for a routine sample or for a routine lesson. If the professor in an auditorium asks you a question and you were not aware that you were going to be asked questions, you might do worse than if you have the exam 2 months later. So WADA, at least in 2 rounds, adds 5 samples to regular samples. Samples we do not know that we are being tested by. And they are spiked, or they are coming from the same type of studies as the previous ones. And again, we are evaluated if we analyze those correctly. So, in total we have quite a lot of sample, and more of these samples are from the double-blind type. So, the blind type is going down, and more we are being tested by double blinds. The intent is by 2020 that we will be tested at least every month by a double-blind sample. Now, if we make a mistake, we get penalty points. If you miss something which is not present in a sample, you get 10 penalty points. If you detect something which is not present, you're kicked out immediately. You've got a false positive. If you missed 2 substances in a single round, which you needed to detect, you're out, you're suspended. If you miss 3 per year, you are suspended. If you get some steroid profiling parameters or pHs or specific gravity wrong, you get penalty points. In total, if you get 25 penalty points in a year, you are suspended. This means that you have a very stringent system. And if you're looking at the current world, we have one lab which is revoked, Moscow. All of you have heard about this. This is not because they had false negatives or false positives. It is because of mass fraud at that lab. But we also have 5 labs which are suspended, because I'm very glad to say that this night we received message that Madrid, which is still suspended here, its suspension has been taken away. So it has been lifted. Madrid is again an accredited lab. By the way, Madrid was suspended not because of errors. Madrid was suspended because Spain as a country was WADA code non-compliant. And one of the rules says that if you want to have a lab in your country needs to be code compliant. So Madrid was suspended because of the country, not because of the lab. But nevertheless, 5 labs currently are suspended. Earlier this year, 7 were still suspended. So it's a very stringent system if you know that we only have 34 labs in total. And it's put in place. It is a good system to check this. Now what do we need to detect? I'm going to go through this very fast. We have a wide range of substances. First of all, substances which are prohibited, as you have heard, at all times, meaning in competition and out of competition. And between brackets, you see the WADA's MRPLs, minimum required performance limit, so the concentrations we need to be able to detect in every single sample. It is demanded from us that our limits of detection are at least half of this or lower. So if Professor Vete was talking about nanogram per ml, that's a sugar cube in an Olympic swimming pool, for clenbuterol, we need to be able to detect a sugar cube in 40 Olympic swimming pools. That's as low as we need to go. So for other substances, it is less stringent. But for clenbuterol particularly, it's 1 sugar cube of clenbuterol in 40 Olympic swimming pools. Now, we've had several classes of substances. The non-approved, as you have heard, those are really trending. Substances which are still undergoing clinical phase trials or coming from the veterinary field, which are not approved for use by humans. So it's not only human substances. And then we have several classes of prohibited methods. We've been very well introduced about gene doping by Professor Huisma, and it needs to be said, yes, we can detect gene doping in a certain way. The method of Anna Bautina is in place in several laboratories. It is not a technical reason why it has not been put into practice. It is more a political reason for the moment why it's not being put into practice. So a selected number of labs have this method, but we are waiting for the green light to apply it to real samples. Some other methods are improving oxygen transport. This is, for example, blood transfusion and chemical and physical manipulation. This might be substituting urine by clean urine, for which, of course, the doping control officer does some checks, performs some checks that the person is actually really urinating into the bottle and is not using a condom like clean urine, for example. But another one might be chemical manipulation, the addition of washing powder to urine, because washing powder contains proteases. Proteases will degrade proteins, and EPO, for example, is a protein. So you would not able to detect EPO in urine if an athlete adds washing powder to its urine. That's also why we have a detection method in our lab for washing powder. So it's not only about what you would expect, drugs and the general conception of English, medication and drugs, but it's also other stuff which might be problematic. In competition, meaning just prior to or just after a sporting event, a number of other classes are being added. And these are mainly substances which are only active for a very short time. And that's also why the detection levels, I mean the MRPLs which we need to reach, are higher. Because the concentrations you are likely to detect in the urine are higher because they have a very short period of action. And we do not want to punish athletes which have used cannabis, for example, during a training period, 3 weeks afterwards, when they compete at a competition. So the detection levels go up, or even the thresholds go up. Alcohol and beta blockers, as you've heard, only prohibited in certain sports where they have a performance enhancing effect, or where they might pose a very big risk for the sportsman, or, for example, also the people watching the sport. Think about driving a car in Formula 1. If the guy is drunk behind the wheel, you run a high risk. So that's why in motorized sports, alcohol is prohibited. Having said that, we test for the use of alcohol in every single sample currently, because the use of alcohol might change your steroid profile. And that is important as steroid profiling has become part of the biological passport. So we don't give a sanction because an athlete has been drinking a beer, otherwise Philippe Gilbert would have to give back his victory for the Amstel Gold Race, as he clearly drank some alcohol on the stage, but it can affect your steroid profiling, so we need to be aware of this. Now, the challenges we are having, and I'm going to mainly talk about urine, because 99% of the substances we are detecting are detected currently in urine. There's a very low number of substances, growth hormone, blood transfusion, for which we aim at blood for the moment. All of the others are in urine. What are our challenges? Well, actually we get a relatively low amount of urine, 60 milliliters, and we need to be able to detect very low levels of banned substances. Fast reporting is every now and then required. Normally we have 10 working days, but for major events, Olympic Games, World Championships, athletics, we only get 24 hours. So it needs to go fast. What low LODs? Currently, we need to detect a wide range of metabolites. An emphasis has been put on that we need to add long-term metabolites as well. This is very effective. If we think about retesting, for example, of the Beijing and London Olympics, you have quite a lot of positive samples coming out of that. Why? Because we have discovered 2 new metabolites which we did not know of before. Well, actually we only discovered 1 new one. The main metabolite for dihydrochloromethyl testosterone, oral turinabol, which gives a high number of positives. The other one is that we have discovered a new methodology to detect 3'-hydroxystanosol glucuronide, and I'm coming back to that one later. As you've seen earlier, Van Johnson was positive for stanosol, so it's a substance for which we knew the metabolism already in 1988, but because actually Van Johnson was positive also for 3'-hydroxystanosol. But we've changed the methodology to detect that. What else? Well, of course we need the highest level of certainty. We cannot accuse an athlete of having doped when he did not do so. For qualitative methods, this means we need to be sure about the identity, and as Professor Piquet has clearly shown, GCMS or LCMS are the best techniques. Combining chromatography with mass spectrometry, you get the perfect system. For quantitative methods, of course, we need to go for measurement uncertainty. We need to be sure about the quantity. And if you're looking at our measurement uncertainty, you will see that in general, that needs to be between 5 and 10 to 15%, which is extremely stringent. Everybody who has ever done quantitative analysis at these low levels, I can assure you this is extremely stringent. And we are evaluated for this as well, that our measurement uncertainty is in line. When WADA sends us samples, we are greatly evaluated for this. If our uncertainty is greater than this, or we report concentrations which are not in line with this maximum uncertainty, we get the same penalty points as a false negative. So it's quite easy to get kicked out, as I've seen. Another challenge, of course, is the prohibited list. The prohibited list, which changes every year. They add new substances, some of them are designer, black market substances, substances which are in clinical phase trial, or even for some proteins, generics, which cause some problems, because in general for small substances, generics, the substance is the same. This is not the same if you have proteins. Your isoform pattern, for example, might change between different types of EPO which are on the market. Another thing is that the list as such is not a limitative list. It also includes substances with similar chemical structure or pharmacology. So even if the list stays the same, the content of the list can change during a year. Earlier we had a question about ITPP. I can tell you, yes, ITPP is prohibited. It is classified under the blood boosting substances. So it's not only in horse doping we test for ITPP, but also in human doping. And another question from the audience about horse doping or animal. No, that is not covered by WADA. Horse doping is covered either in racing by the International Federation for Horse Racing Authorities or in other equestrian events by the FEI, the Fédération Équestre Internationale, who cooperate with WADA, and they themselves, the IFHA and the FEI, are now getting together to harmonize their rules as well, to get to a single list, a single set of rules within horse doping. And I'm not even talking about the pigeons or the mad cow fights they have in Switzerland, so there are still other organizations as well, according to which sport. The challenges we still have otherwise is that not only substances are being added, but every now and then also new classes are being added. The SARMs, for example, were added in 2008. Why? Because anti-doping labs had spotted these in patent applications and in first scientific publications about SARMs, and we had immediately said we need to start analyzing for these substances. So we have synthesized these substances ourselves. We have done in vitro metabolism studies for these ourselves. We've added them to our methods, and these substances are not even on the regular market. But by 2010, we had spotted the black market product. By 2011, we have had positives, real positives of athletes buying black market SARMs via the internet. Non-approved substances, well, all of these, you could say, are new classes. You never know what it is, and we have quite a few of these. We had, for example, in the Paris lab, we had, before it was on the market, FG4592, now known as roxadustat, who was detected there, before it was on the market. So we have quite a few of these, and I'm not going to tell you which ones we're monitoring, but we're monitoring quite a few of these, hoping that at some point we will catch athletes who think they're using something which is undetectable. Another problem we have is we need to differentiate for some substances between endogenous and exogenous. This is, for example, for testosterone. So we have IRMS, the isotope ratio mass spectrometry, who does this mainly for anabolic steroids, and then we have the biological passport. The biological passport, which has currently 2 modules which are being used. One is the blood passport, looking at blood parameters for the use of either blood transfusion or EPO or any blood boosting methodology, and the steroid profile. The steroid profile module, which looks at the use of endogenous or natural steroids and anything which boosts that or which might suppress some pathways of metabolism. But that biological passport will be extended with other modules. The endocrine module, for example, for growth hormone, or perhaps, if it would be necessary, at some point also a genetic module. But that's still a far distant future, but it might be possible to monitor that. Sometimes also old classes will get a new focus. Whenever we find a solution, for example, we have a detection method for EPO, well, athletes shift pattern and they change back to blood transfusion, which had largely been stopped in the 1990s when EPO became available. As soon as EPO became detectable, they used blood transfusion again. Another thing which we are confronted with at our labs, much more than at any other type of lab, I guess, is this, media attention. This is not something we long for, this is not something we strive for, but of course every now and then we need to help the media in putting the right emphasis on the right stuff. So what do we have as techniques today? A very wide range of techniques, extremely wide. We have gas chromatography coupled to mass spectrometry and liquid chromatography coupled to mass spectrometry. The gold standard, as Professor Witte said. I only don't agree with him that gas chromatography needs to be abandoned. I really think that they are complementary techniques, and I will even show you that gas chromatography, the last 2 years, has made a real good comeback. So it looks as if it was dying, but it has been revived, and it's actually, in my opinion, currently complementary to LCMS. Not better, not worse, it's complementary. Immunological tests. We have quite a few immunological tests, although we try to abandon those. We have them for growth hormone and the female pregnancy hormone. We also have combinations of separation techniques, electrophoresis, SAR-page, SDS-page, combined with chemiluminescence, isotope ratio mass spectrometry, flow cytometry even, to detect, for example, homologous blood transfusion. We differentiate between 2 different types of blood cells. So you know that if you have 2 different types of red blood cells, they must have come from different individuals. So we have proof of homologous blood transfusion. And we have hematology analyzers for the blood passport. But if we look at the complete list now without pictures, anything in green can be done by chromatography, coupled to mass spectrometry. So immediately it becomes clear that out of the list, almost any class can be targeted by these 2 techniques. And that's why they are the gold standard. Not only because of their selectivity and their specificity, but also because they can cover most classes and most substances within those classes. And even gene doping, indirectly you might say, might be covered by chromatography and mass spectrometry. If you have an indirect method, for example the steroid passport or the blood passport, whatever, might be an indirect effect of gene doping, you could cover this as well. Just to give you an idea, for example, if we were talking about hormones and related, the method for HCG, for example, human chorionic gonadotrophin, we can now do as well with mass spectrometry, so we don't need an immunological analyzer anymore. The only difficulty is using an immunological analyzer. The cost is about 4 euros per sample. If you use LCMS for this one, it's about 400 euros per sample. So we can't do every sample via LCMS so far. The trends, and now I become very technical, we have made a shift from GCMS, single quad technique, to GCM-SMS. So mass spectrometry followed by mass spectrometry fragmentation of a product ion. Why? Because it's much more sensitive and it's much more selective. For LCMS, which was never used as single MS, it was always MS-MS, otherwise you don't have enough selectivity and specificity and sensitivity. We have changed, and several other labs have, many of us now have changed to high-resolution mass spectrometry. High-resolution mass spectrometry, it's more not sensitive, it's a little bit less sensitive in general, but it gives you a much more flexibility to add new substances, and most importantly, you can do retrospective analysis. What is meant with this? So when you analyze a sample right now on an LC, high resolution mass spectrometer, and most labs use Orbitrap technology because it is the most sensitive and has the best mass accuracy. If you analyze a sample now on such an instrument, you gain data. Afterwards, you need to know is a substance present or not, so you need to filter that data. And you can only filter on the substances you are aware about, that they might be present in urine. So you set certain filter parameters looking at, is amphetamine present, is stanozolol present. You do this, and that's it. If after 6 months, suddenly somebody tells you, wait, 6 months ago there was a new substance on the market, prostanosol. You can re-evaluate the data on your computer to see if prostanosol was present in the urine as well. This is different from the old technique, LCMS, where before you started with the analysis, you needed to say, I'm going to look for stanozolol, I'm going to look for amphetamine. You didn't know about prostanosol, you would never be able to see it. With a high resolution, which is a little bit less sensitive, you can add substances after you've analyzed it. Do re-evaluation of all your data. And this is important because now we can store samples for 10 years. As you've heard from the Beijing and London Olympics, they will reanalyze samples for new substances and new metabolites. But they need to take the samples from the freezer and reanalyze them. With this technology, you can reevaluate your data and then select the samples you need to get out of your fridge. So it saves a lot of costs. We also have other separation techniques, not only GC and LC, we also have isoelectric focusing or SDS-based, SAR-based for some other proteins like EPO. Another thing we've done is we've moved from standalone values. Samples are arriving in the lab anonymous. It's a condition for analysis. If the identity of an athlete is present on the doping control forms or can be linked to a sample, anti-doping labs will not analyze that sample. A sample needs to be anonymous. So previously what we could do is we had the analysis results and we could compare certain values, for example the steroid profile, with population statistics. These days we report the values into a database called ANNOs via the internet, and that database gives us feedback. We get feedback because an anonymous sample, because of the sample code and the data given by the organization who went for the sample collection, can be linked to an individual athlete. And so all the data we enter can be linked to previously acquired data. And so you get the response, the current data is not compatible statistically with the previous data of that athlete. So you're moving from a population-based statistics to an individual-based statistics. And this is the steroid profile, for example, the biological passport, where you see here in red, these upper limits, they go up. The blue dots even go outside. This is not normal. This is an athlete whose values are abnormal compared to his previous, much more stable parameters here. So you know you need to target that athlete, do additional analysis for that athlete. As I've said, we've expanded the number of metabolites we're looking for because we want to cover a whole big range, as we have zero tolerance for most substances. So we have short-term metabolites, meaning excreted shortly after you've used it, but we also have long-term metabolites. Looking for metabolites is also legally better because, as you've heard, some athletes will claim, oh, that substance was either spiked to my urine or spiked to my drink. By looking at the different metabolites, you can try to corroborate whether or not that is true. The high resolution will also allow us to re-evaluate more flexible, but essentially you can also reanalyze samples for new metabolites using any technique. And this is a huge success. 95% of the positives coming out for the Olympic retesting of London and Beijing are dihydrochloromethyltestosterone and stanozolol, those two substances. For those two substances, we made a huge step in detection time. There's another substance coming up quite shortly, and you're getting the sneak preview on this one. So, not only re-evaluation according to metabolites, but also according to the methodology. Because previously we could only detect phase 1 metabolites after they had been deconjugated. Now, thanks to LCMS, but GCMS is coming for this, I promise you, we can also detect intact phase 2 metabolites using dilute and shoot or solid phase extraction techniques, eventually even liquid-liquid extraction, although the recovery is not that good. Something else we're doing these days, which we didn't do 5 years ago, is pre-analytical phase monitoring. And here we are really running behind clinical laboratories which have been doing that for decades. Now, why do we do this? Because of the steroid profile and because of the biological passport. All of these parameters, the fact that you have degradation, for example, can have an effect of the steroid passport, and therefore we cannot suspend or claim that an athlete is more at risk for using endogenous steroids. Now, one of the successes is that we have re-evaluated technology for the same problem. Stanozolol, if you take it, is mainly metabolized to some hydroxylated stanozolol metabolites, including 3'-hydroxystanozolol glucuronide. Now, the traditional technique, how you do it, is you take urine, you hydrolyze it with beta-glucuronidase, the glucuronide fraction gets cleaved off, and you get the phase 1 metabolite, which you can then extract, derivatize, and analyze via GCMS. This was how it was done in the 1990s, up until now, and you have detection limits even now with GCM-SMS, which are in the range of 5 nanograms per ml. When we switched to LCMS for this substance, we exactly took the same methodology, and we switched to LCMS, detection limits of 1 nanogram per ml, but it is not needed with LCMS to look for the phase 1 and to do a deconjugation. If you look to the intact glucuronide, with LCMS you can go to 10 picograms per ml. And this is why we have so many stanozolol positives these days. Summarizing what happens in our lab in practice. For GCMS, we've made a big change. Changing from GCMS, we were the first lab to do so. Now all labs do it this way, from GCMS to triple quadrupole mass spectrometry, which meant that we had in GCMS 60 substances, now we have 200. In 2015, and this is why GCMS is coming back, we've changed from EI, electron impact, to CI, which gives you a great increase in sensitivity. It has predictable fragmentation and it delivers you new information on substances. So in 2017 we have more than 250 target metabolites in this methodology, and we have detected multiple new long-term metabolites. Just to give you an idea, for oxymestrone, using this technique, CI, we go from 4 days of detection to 44 days of detection. And oxymestrone, by the way, is not detectable via LCMS, because it's 4-hydroxylated steroids and they do not work ionization-wise. For LCMS, we've changed from liquid-liquid extraction to dilute and shoot, from triple quad to high resolution, giving us more flexibility. We were the first lab in 2011 to use this in practice, over 200 targets. In 2013, we changed again to adding dilute and shoot and extraction to increase sensitivity. In 2017, LCMS, and now Professor Vite is going to laugh or smile, is still winning, over 300 targets, but in general we now have over 550 targets in our lab for doping. In summary, if you want quality, you need to have ISO accreditation for continuity, you have to have stringent quality rules, and very importantly, independent control, meaning you need to check that what labs claim are true. And this is the case for anti-doping labs. You need to take care of and take advantage of technological advances, and we do this very rapidly. Also the internet, not only technology you can buy, and not only the technology needs to advance, but also the methodology needs to advance. Do not just take for granted that by buying a new instrument, applying the same old methods will give you most gain. Finally, I would like to thank all of you for your attention, but also my colleagues at DoColab, my partner labs. We form an organization called WADS, and of course the two organizations which are funding most of our research, being WADA and the Partnership for Clean Competition. Thank you.
Thank you for your talk. We have time for one question. Not the case. I would like to. Oh, sorry.
Can you please confirm that diet is still a defense?
Diet, a defense.
That is, for example, if there were a method by what you eat or don't eat to both thin the blood and oxygenate the blood, that's a defense. Or if you could drink some herbal tea that would make you pee more, that's a defense too. I understood from a slide, I guess it was your colleague's presentation, that if there's a detection, positive detection, that it is possible to defend oneself with the idea that you're still free to choose what you eat or don't eat.
Okay, so you're still free to choose what you eat or don't eat, as long as it doesn't contain any doping agent. So that's the key. So you're not allowed to eat cocaine leaves, for example, in competition, because that would be doping. Having said that, there are many kinds of defense we are confronted with. Some of them, of course, are ridiculous at first, but then prove to be true. Using diet has been used for particular cases. For example, I had a whiskey after this stage of the race, and therefore my TE ratio was high. But I didn't explain for that particular rider who lost the yellow jersey in the Tour de France, because there was IRMS, and your diet does not in general influence IRMS, unless you completely change your diet, going from carbon 3 to carbon 4 type plants, but that will also be detected in other steroids which are concurrently analyzed. Having said that, you could claim that you were positive for octopamine because you ate a lot of lobster. And so we do experiments, unfortunately not in my lab, by eating lobster and checking whether or not it makes sense. Currently, for example, there's a new beta-2 agonist on the list, hygenamine. And so, although we need to be able to detect very low levels of hygenamine, we have been instructed not to report hygenamine cases unless the concentration is 10 nanogram per ml. because if you eat lotus root in high amounts, you can get hygenemine into your urine. So your diet can be a defense, and sometimes it works. There were Brazilian long-distance swimmers who got off for nandrolone because they could show that if you ate a lot of offal from boars, you might get some natural nandrolone present in the offal of the boars, which would mean that you get a positive test. So that's why also we have an RMS for nandrolone. So whenever these things come up, we need to investigate and we need to find a solution. And sometimes the things they claim are true, and we need to adjust the rules. Find a solution, adjust rules. Other times it is complete rubbish. We have, for example, a myth currently that if you drink green tea, your steroid profile is influenced. That is false. Unfortunately, that's an experiment we have done in our lab. Drink a lot of green tea. I would have opted for the lobster, but we got the green tea. But for example, if you drink alcohol, and perhaps in the reception there will be some alcohol, I can assure you, your TE ratio, testosterone to epitestosterone ratio in your urine, will go up. For those of you who think that your testosterone production goes up, this is not the case. It's the excretion of testosterone which is promoted and the excretion of epitestosterone which is decreased. So in the urine there's an effect, biologically there's no effect. Otherwise all of us would have a lot of muscle because we were drinking a lot of alcohol. This is not the case.
Other questions? If not the case, I think we will now close the meeting because we are